Welcome everyone to the final installment of the 10.1 class notes, where we're going to talk about the type 1 and type 2 errors, and then we're going to recap all of the steps that we've seen for hypothesis testing before we get into 10.2, where we're actually going to try some examples for it. What we have with the type 1 error, that's when you reject the null hypothesis when the null hypothesis actually was true. And a type 2 error is when you fail to reject the null hypothesis but the alternative hypothesis actually was the one that was true, so we should have rejected it. And I think that it will be very clear when we see this example, and this is the example that I think of to remember which is which between the null hypothesis, or rather between the type 1 error and the type 2 error. So we will treat an example this way where we have the null hypothesis is that the defendant is innocent, so you have some type of a trial going on. And of course, in the United States, we're supposed to be innocent until we're proven guilty. So the default is that a person who is being suspected of a crime is innocent. There must be then sufficient evidence put forth to reject that, to reject the null hypothesis, and to conclude that the person actually is guilty. So if we make a type 1 error in this case, and I'll put it on this page, type 1 error in this case is to reject the null hypothesis when it's actually true. So that would be to find the person guilty when they are actually innocent. We find them guilty, but they are innocent. So this would be a false conviction, and we're sending an innocent person to jail right now. Well, we're assuming that this is such a case where the penalty would actually be jail in particular. Imagine if the penalty was a death penalty. This would be where you falsely put someone to death. That's not very good. Type 2 error would be when you fail to reject the null hypothesis. So failing to reject the null hypothesis in this case would be to conclude that the person actually is innocent. So this would be innocent verdict, but they are guilty. And what I like to think about in this one, not that I like to think about false convictions and so forth, but which one of these, in your opinion, do you think is worse? Would it be to have somebody who is innocent be convicted of a crime that they did not do, and then they're going to be punished for that? I think that sounds very terrible. What about type 2, where they're actually guilty of something, but they get found innocent because there just was not enough evidence somehow to convict them? To me, it seems worse. It seems like a worse injustice, the type 1 error, where somebody is innocent, but then they get found guilty and they get convicted of the crime that they did not do. That seems worse to me. I always remember that type 1 error is the one that's worse in this case, and that can help me remember on the spot which is which between type 1 and type 2. So if you find out another way to remember that, then we would all be interested to hear about it. But we have just filled in these blanks on the previous page, talking about type 1 and type 2 with respect to innocent and guilty. What about this one? We will set up some null hypothesis, alternative hypothesis, and then talk about the errors. So here a reporter claims that more than 50% of workers find their jobs through networking. That means that the hypothesis that we're testing, or the claim that we are testing, is that the proportion is more than 50%. We should then have our default one, which is the null hypothesis, is going to be that's equal to 50%. In that case, a type 1, remember, that's whenever we reject the null hypothesis, but actually we should not have done so. So for type 1, what we'd be saying is we would conclude in this case that actually more than 50%, or I was going to put 0.5, but I'll just say 50%. More than 50% of workers find their jobs through networking, but actually only 50% do. So it's not more, it's actually only 50% in reality, but we rejected that and went with the alternative hypothesis. The type 2 would be whenever we conclude, because type 2 would be that we do not reject the null hypothesis, but actually we should have. So we will conclude that 50% of workers find their jobs through networking. Just don't want to write all of it, but more than 50% do. And a lot of these examples, it's kind of goofy to think about these errors because they don't seem like that bad of errors. It's like, who cares really if more than 50% of people find their jobs through networking or less, or it's equal? It's not really that impactful. But if we're talking about, efficacy of like a medication, or, the likelihood of getting some kind of side effects that are very damaging, that it's going to maim someone or something like that, that's when these errors, or even the example about, false convictions or something like that, those kind of errors, whenever they're really impacting someone's life, it makes them seem more significant. In these cases, whether these errors are really gonna, make too big of a deal. Of course, we don't want to make errors whenever we're doing science and we're doing math stuff like that. We don't want to have errors. But here we're talking about how much those errors are actually going to affect someone is maybe, it depends a lot on the context. So here, when we have a sociologist is claiming that the average age when teachers begin working is less than 15. So probably we're talking about, some situation where we're going to be making some legislation or something about child labor or something like that. I don't know, that it could maybe affect someone. But here, the alternative hypothesis, we're looking for the average age should be less than 15. The null hypothesis then is that the average age should be equal to 15. Type 1 error would be we reject the null hypothesis. So we conclude that the mean is less than 15, but the mean actually is equal to 15. And in the case of type 2 error, we're going to fail to reject the null hypothesis. And so this would be, if we fail to reject it, then we would be concluding that the null hypothesis actually is the true one. Concluding, we probably don't want to say ing, conclude that the mean age whenever children start working is 15, but actually it's less than 15. So that's how that would go. Those are the errors. And now let's just recap what we saw as far as the steps for hypothesis testing. First, we have to figure out what actually is the claim that we're testing in the first place. What is going to be the hypothesis to test? That must be the first thing to do before we actually test a hypothesis. And then we want to be sure that we're using the right symbols, of course. Mean versus proportion symbol, and then also keeping in mind that the alternative, it should never use an equal sign, so we don't want less than or equal, greater than or equal. We want to avoid those, just so that these hypotheses are disjoint from each other. And then we will determine the level of significance, and that's going to be, actually, remember, the level of significance is the probability to make a type 1 error. So if we want to have a lower probability to make such an error, for example, the probability to falsely convict someone who's innocent, if we want that to be very, very low chance, we want to use a smaller level of significance. So this is going to be an arbitrary value that's chosen by the researcher, depending on how much they want to avoid making a type 1 error. And then the critical value, of course, is the z or t value that corresponds to this level, which it also has to do with whether it's a left tail or right tail, but the critical value is what separates the critical region, which has an area equal to alpha. That's the area of this left-tailed test, for example. And then we will take a sample. We will find the test statistic for that sample. We will either find the z-score of that proportion, or else the t-score for the mean. And then we can draw some type of a graph, which I've already started drawing one here, where we will draw for example, if we're doing a two-tailed test, we will draw this critical region and we will label what is the critical value that separates these regions. And then whenever we label the test statistic, for example, if the test statistic is here, then we will not reject the null hypothesis. If the test statistic is in one of these tails over here, then we actually will reject the null hypothesis. Next, we should state the p-value, which remember p stands for probability. That will be the probability to get such a test statistic, and if it's less than the level of significance, then we will say if that probability is less than the level of significance, it was so improbable, it was statistically significant enough that we will reject the null hypothesis. And then we will state our decision of whether we're going to reject or not reject the null hypothesis. Here we just see a couple of different approaches where the classical approach would be if the test statistic is in the critical region, then you reject the null hypothesis. There's another way to phrase that basically, which has to do with the p-value and the level of significance, but these are the same idea. It's just whether you're talking about the critical value or the critical region. And it's kind of, if you look at these, I hope that you're getting the difference over here. It kind of draws into question the step number 5. Basically, you could omit step number 5 if you're going with the classical value because the p-value doesn't really matter. We understand that the p-value is going to be used as our criteria if we want to compare it to the level of significance versus comparing our test statistic with the critical region. That's kind of, I don't want to be too confusing, but we'll see probably a couple of examples where we use the classical approach versus the p-value approach, and it should be all fine. And then last but not least, we would write out our conclusion using the correct sort of, here we have, of course, these templates for how we would phrase such a conclusion. And so you don't have to be, it's not an English class, it's very scientific. You don't have to be imaginative when you're writing these conclusions. You can just use the formula, plug in the claim, you're going to get a good conclusion out of that one. So that does it for 10.1. We're going to get started in 10.2 and shortly, which is going to be actually testing some hypotheses, in this case for population proportions. And so stay tuned for that. And thank you guys for watching.